Let's have a look at the atomic structure that we use at A level. Now, you'll remember from GCSE that when we draw the atomic structure of something like, for example, calcium, we use a model which various people call dot and cross or Bohr model. And it's based on the model of the atom where electrons are orbiting in fixed electron shells. And it's credited to Niels Bohr. And this works really well to explain, for example, why calcium forms a 2+ ion, because we have these 2 electrons on the outer shell, and of course, when we take them away, we end up with an ion with a 2+ charge as those 2 electrons have been removed. And that works really well for elements 1 to 20, but it's not a perfect model, and it tends to break after element 20 because if we take copper as an example, and we look at what would happen if we tried to draw the Bohr model out, we have 2 electrons in the middle, we have 8, then we have 8, then we have 18. We end up with a little bit of a difficulty here because we actually have a situation where trying to make this into an ion, we've got 2 options. We could take a load of electrons away, like that, and make 11 plus, which doesn't exist. So that one's not going to work. And we could alternatively try to fill that shell by putting 7 electrons on to fill the shell. And it doesn't work because copper doesn't form a 7- ion, and copper doesn't equally form an 11+ ion. So we can't really explain the chemistry of copper particularly well using the Bohr model. So we've got to find a different way to show atomic structure which works better. The model that we're going to use is based on the Schrödinger equation. And the Schrödinger equation can be solved for an atom of hydrogen or something like that, and it generates some quantum numbers which we can use to describe various properties of an atom. So, first of all, this is an imaginary 2D distance, and I just want to show you that if we had a wave that was oscillating in this gap between the 2 lines, then we would have something that could oscillate a little bit like this, where we have up and down. So it's kind of going wibble, wobble, wibble, wobble, wibble, wobble. And we could also take a wave and we could put it into this gap. But we could say, okay, well, we'll have this like this. And then we can have this like this. And so it's going wibble, wobble, wibble, wobble, wibble, wobble, if you like. And then we can look at this further. We can say, okay, well, what if we did this? And then again, we're having a wave, which is again oscillating between where the red and the blue are. And we can carry this on pretty much infinitely. I mean, mathematically speaking, we can be infinite about this. Because what we're doing here is we are fitting waves into this gap where they are either a full wavelength or a half wavelength or a multiple thereof to fit nicely into that gap. Now, what we don't get is we don't get anything in between this and this. And this is the idea of a fixed energy level, because as you know, with a wave, the higher the frequency, the more energy there is. Okay, so you can see that this wave here that's trapped in this space is the lowest energy of these. Now we can use the Schrödinger equation to predict these patterns, and the number that's assigned to each of these places that we could fit a wave is called the principal quantum number. And what it represents is it represents an energy level that an electron can exist in, because an electron can be thought of as both a particle and a wave. So we're treating it as a wave here. We're treating it as in this is the lowest energy that an electron could possibly have. So we're going to call that principal quantum number 1. And then we're going to call this one 2, 3, 4. And this is the same thing as saying this is energy level 1, this is energy level 2, this is energy level 3, this is energy level 4. Or, as we tend to call it, shell 1, shell 2, shell 3, shell 4, when we're talking about electron shells. And so the principal quantum number tells you the energy level of an electron. And we can see that we have fixed energy levels, just like we did in the Bohr model. So more numbers can be generated by the Schrödinger equation rather than just having an energy level, because what we find is that we have angular momentum as a quantum number as well. And that is or could be any number up to 1 less than the principal quantum number. Okay, so in, for example, energy level 1, n minus 1 is 0, so the only possible number is 0. So we only have one possible value that could be. And in principal quantum number 2, n minus 1 is 1, so we have 0 and 1. So we have 2 possible angular momentum quantum numbers that this could be. And so basically we are increasing the number of possible numbers by 1 every time we go up an energy level. So what does it actually mean? What it means is that each of these numbers is attached to a certain shape. And when we have the number 0 here, we actually get a shape which is spherical. Now we can plot the 3D shape by taking the square of the wave function that comes out of the Schrödinger equation, but we don't need to worry about the nuts and bolts. This is the best sphere I can do in 2D. But we have a spherical shape for this one. We have, for the next one, a slightly different shape, which is this one. And it can be called a dumbbell sort of shape. And these two shapes you need to be able to draw. Okay, we call this one an S orbital. Okay, and the S stands for simple. We call this one a P orbital, and the S stands for principal. And then as we go down, we add more. The next one has a slightly complicated shape to draw, and I tried to draw them earlier and I couldn't. So I've got some models instead. We have this sort of shape as our D. That one in particular is quite weird. And so we have various different shapes that could be. But we don't need to be able to draw those for A-level. And then number 3, we could continue. There's such a thing as an F-shape orbital, and those are really tricky to draw. I'll put a link in the description for some better pictures from another website where someone's actually done a computer rendering of them, so you can see what shapes they would be, but I can't draw them. So these numbers give us the different possible shapes. And as I said, in the first one, we only have 0. So we only have S orbitals in energy level 1. And in energy level 2, we can have S and P. And in energy level 3, we can have S, P, and D. And in energy level 4, we can have S, P, D, and F. So each of these energy levels has a certain type of orbital fixed to it. And as we go up the energy levels, we add one more, S, P, D, F. There are more numbers that we can calculate from the Schrödinger equation, and one of them is the magnetic quantum number. What this does is it tells us how many of each orbital there is. The idea of this number is that it is equal to plus or minus L and every number in between. So plus or minus 0 for this first one, Well, plus 0 and minus 0 are the same, and there's nothing in between them because they are just 0. So there is only one possible combination. So there is only ever in an electron shell one s orbital. With the next one, with p, we have L is 1, so we can have -1 to +1 and all of the numbers in between. So we could have -1, 0, and +1. That's 3 p orbitals. So there are 3 p orbitals, and they are, well, this one would be the -1, and then you've got the 0, and then we've got the +1 in a different orientation. They're just in different orientations. We don't need to worry about which one is which, but we do need to worry about the fact that there are 3. They're all the same shape, and they're all kind of superimposed on top of each other. With the D, I showed you the models earlier, but we've got +2 all the way down to -2. So we've got -2, -1, 0, +1, +2 is 5 d orbitals. There's this one, this one, this one, this one, and this one. We don't really need to worry about which one is which, but we need to know that there are 5 of them. And then F, if we take the same idea, -3 all the way to +3, so 2n plus 1 would be 2n would be 6, and then +1 would be 7. So we got 7 possible F orbitals. In energy level 1, we only have 1 possible s shell. In energy level 2, we have 1 s shell, and we have 3 p orbitals. In our third shell, we have 1 s, 3 p's, 5 d's. And then in 4, we have 1 s, 3 p's, 5 d's, and 7 f's. Now, an orbital can hold up to 2 electrons. It's the region around a nucleus which can hold up to 2 electrons. So when all of these orbitals are full, 1 s orbital can hold 2 electrons, so there would be 2 electrons in shell 1. Same as in our Bohr model, if you remember our dot and cross diagram, we have 2 electrons in shell 1. So in our second shell, we have 1 s orbital and 3 p orbitals. That means there are 4 orbitals in total. 4 orbitals, 2 electrons each, gives us 8. That's our second shell has 8 electrons in, same as our Bohr model. Now this is where we see a difference. We find that in energy level 3, or electron shell 3, we have 1 s orbital, 5 d orbitals, and 3 p orbitals. So that means that there are 9 orbitals in total, and 9 orbitals multiplied by 2 for 2 electrons in each is 18 electrons. So actually, the third shell we can fit 18 electrons into. Now that's different to our Bohr model, because we tend to go 2, 8, 8 with the rules for filling that up. And we'll see how this actually works on an atom and filling the electrons into an atom in a future video. So, fourth shell, finally, if we look at this, we've got 1 s and 3 p's, that's 4 in total, and 5 d's, so that makes 9 in total, and then 7 f's, which means that we have 16. 16 multiplied by 2 gives us 32 electrons. So we've got 32 electrons in our fourth shell. And so we have a new and more sophisticated model of the atom. And we're going to see how to construct an electron configuration using this, again, as I say, in a future video, and I'll put the link up here.